All right. So first off, apologies for forgetting I forgot my microphone, so I'm kind of just speaking into my laptop, which I hope the audio is fine. I also have a student here in my office as well, so I'm gonna try to talk to you guys online, to you guys on the office, and hopefully we'll work it out pretty well. So I do want to start by covering some of the basics. I'm going to ask if you can please mute yourselves, Hope and Kelly, just so that the audio doesn't kind of mess up a little bit. And Diego and Andy, just try to mute yourselves if you can. You can unmute yourselves if you want to speak. That'll be great. But for now, I'm just going to mute everyone until you're ready to talk and all that stuff. Okay. Anyway, let's start by talking about what we're going to cover. So this math review really covers derivatives, integrals, vector calculus, ordinary differential equations, and some other miscellaneous topics. The purpose of this review is not really to reteach you calculus because you've already taken that class. The purpose is really to show you how that class could relate or will relate to fluid mechanics, right? Now, I'm not much of a numbers person. I definitely prefer that you understand the concepts first. So I would like to start talking in terms of concepts. I really want to go over some of the basic concepts for us before we actually start throwing in numbers, okay? So the first thing I'm going to start with is derivatives. By the way, this is my first time using this, this pad or writing pad or whatever. You know that if you're in my class, you know that I like whiteboards and pen and paper, but I think this is easier just for today. Okay, so I want to start by talking about derivatives. Jesus Christ, this is actually really hard to write on. I should have practiced before we started. My goodness. All right, I want to start by talking about derivatives, okay? And we've all heard about derivatives before. Like, I think most of you have already solved derivatives in your calculus classes. Let me just try to write this again. A lot of you have a good idea of how to find specific derivatives of specific functions. I think we all understand that. What I would like for you to understand now is what derivatives really means in terms of a concept. So does anybody know more or less what a derivative is? Not numbers. I mean, just conceptually speaking, what is a derivative? Does anybody have any idea, or has anybody ever heard that before? Okay, I see Mason on the chat says a rate of change. Okay, that's good. And that really is kind of what the concept is, right? A derivative essentially represents a change. Okay, so a derivative represents a change. And change is actually very important in any class in engineering, right? Because we're going to be looking at changes in forces, changes in velocities, changes in pressures, changes in different properties, especially when it comes to fluid mechanics. So a derivative represents change. And of course, this change is a change that we need to understand and that we need to be able to quantify, okay? I want to be a little bit more specific when it comes to derivatives. Yes, they represent change. But if we want to be, if we want to give a full definition, then a derivative really represents how one thing, we can call it a property, a value, a quantity, anything, right? How one thing changes when another thing changes.
Thank you.
Okay. So a derivative represents change with respect to some variable or property. This is very important because really we're not just studying change in and of itself, right? We're not just saying, hey, we're going to look at the change in velocity of a fluid. We don't really care about that, right? We care about how one thing would change as another property changes. If you want to think of it in layman's terms, you can think of a derivative as more or less looking at a cause and effect relationship between two parameters. In other words, as one parameter changes, how does the other one change? What's the effect that one change in a parameter has on another parameter? In order to talk a little bit about derivatives, I think it'll be easier if we kind of agree on some language to use. So I'm going to use the language of functions to represent or to talk about my variables that are dependent. In other words, when a variable changes, when another one changes, I'm just going to call that a function. And I'm going to use the word variable to represent the parameter that I am forcefully changing. So for example, if I want to look at the change in pressure along a fluid, and I am looking at pressure at different positions, I can modify the position and then measure the pressure. And in that case, my function would be my pressure because that's what's changing. And then my variable is my position because that's what I get to change. That's the thing that I control. Now, this is not a catch-all definition, right? But at least it should give us some idea of just to be able to talk in general terms, okay? I want to look at one example of a derivative just to make sure that we understand what change means. Like, we can understand that derivatives represent change. I think it goes a little bit more than that. We should be able to understand how that change can be, or how that change can actually look like in real life, okay? Let's look at Newton's law of viscosity. If you're in my fluids class, we've already covered Newton's law of viscosity. If you're in David's class, not me, the other David's class, then you may not have covered it yet, but who knows? I'm not really up to date with that class, but let's look at Newton's law of viscosity, right? We mentioned that Newton's law of viscosity corresponded of a shear stress, some constant, which we call viscosity, and then this nice property here that we call the velocity gradient or strain rate. Now, looking at how that function, that variable is set out, we have du over dy. Does anybody know what that function actually represents? I mean, just by looking at the variables, what do you think du over dy represents? And u, by the way, u is a velocity and y is simply a position, okay, a space position. So what would du over dy represent?
It would be the velocity, the difference in velocity as you increase or decrease depth.
Okay, yeah, that's good. That's good. It would be the difference in velocity across depth. That's good. Did I write across correctly? Is it 1c or 2c's? Oh. Anyway, it's a difference in velocity across depth. Good. But see, that definition is very, very mathematical. It doesn't really tell me from kind of a physical perspective. It doesn't really tell me what du over dy actually is. So I want to know what du over dy actually means, right? In physical terms, right? If we're actually looking at a fluid particle, right? Some particle of fluid, what does du over dy represent? I mean, we say that this means that the difference in velocity across y. So that means that maybe at one point in the particle is moving at some velocity u1. And then at another point, it's moving at another velocity u2. So what does that difference in velocity mean when it comes to the actual physics of the particle itself? What happens when you have two different velocities at two different points in the same particle? What do you think is going to happen? Andy says rotation. I like that. I like that. I'm going to go a little bit further than that. I wouldn't say specifically rotation, but I would say some deformation, right? Because we're kind of pulling this top part a little bit more than we are pulling this bottom part, assuming that the top part has a greater velocity. So really what we're looking at is some deformation, okay? And the rate of that deformation is the velocity gradient. So yes, mathematically speaking, you can tell me that the velocity gradient is the difference in velocity across y, and you can calculate that. I can give you some numbers, and you can calculate what that derivative is pretty easily, right? I think in class, if I remember correctly, in the class that I teach, I gave you a velocity of, I'm just gonna throw numbers here. I think it was like 400 y, right? Something like that. Mm-hmm. Minus 800 y squared, something like that. And I asked you to find du over dy, and I think all of you are able to find this pretty quickly. The derivative of a constant times a variable is just a constant, and then the derivative of a constant times a variable elevated to the power of something is just a constant times that exponent multiplied by the variable to the power of the exponent minus 1. And again, this is not really a class about memorizing derivatives. You can always find them in tables. I'm not a big fan of memorization, but you can always find those in tables and whatever. And this is fine. However, the important stuff is that you actually understand what this represents. And this actually represents a deformation. So in this class, in fluid mechanics, you really need to understand what the math actually represents physically so that we can start deriving things like expressions, governing equations, etc. There's going to be a lot of derivations in this class, not now, but later, it's going to be a lot of derivations in the class. So it's important that we understand how those derivations actually occur. I mean, it doesn't really take a genius to come up with them. It just takes a good understanding of what's happening physically, okay? Now, let's move on with our topic of derivatives. So I want to talk now a little bit about how we actually form derivatives. I think the important part here is to understand what a differential is, okay? Differential. Now, a lot of you have already seen a differential before. It's just lowercase d applied to some function. You can call it df, for example, where f is my function and d is my differential. A differential is really an infinitesimally small quantity. So this d, this lowercase d here, is simply an operator that I apply to some quantifiable property. Now, when I say quantifiable, what I mean is that the property can be measured numerically. So for example, a quantifiable property can be force, right? You can assign a numerical value to the force, and then you can compare that numerical value to other forces. A quantifiable property cannot really be a color. It could be the wavelength that essentially forms a color, but not a color itself. I can't really say this is red, this is more red, this is less red. I know that in layman's terms, we do use those terms. Yeah, this is very blue, it's not that blue, etc. But really, we can't really quantify numerically. And if we can't quantify numerically, we can't really apply a differential to it. Again, for those of you in optics, you know, I know that you can actually apply numbers to the wavelengths and to the amplitudes, but let's talk in just layman's terms here, okay? You can apply a differential to a quantity, but not to a qualitative property, only to a quantitative property. And what this differential means is a very, very, very small portion. And when I say very, very, very small, I actually mean infinitesimally small. Think of it as infinitely small. Something so small that it's almost zero, but not really zero, not quite zero. If you've taken calculus, you've already studied differentials in the concept of limits, right? You've looked at limits, taking the limit of a function when a function y, when x equals 0, or when x tends towards 0. Really, I want you to think of differentials as really, really, really small portions of a property. Here's the thing, we can actually apply differentials to anything as long as it is quantifiable. So in the previous example, we had done du, and this means a very, very, very tiny, tiny, tiny small change in velocity, okay? So a very, very, very tiny, tiny, tiny portion of velocity. We can apply differentials to positions, a very, 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 very small difference in position. Again, so this is something so small that we can't really quantify it with a number. It needs to be so close to 0, but just not quite there yet. I know that you've already studied differentials before, so let's try to move a little bit forward. The important thing about differentials is that they allow us to use calculus in order to look at how different properties act when we take them at their limits. In other words, when the limit is approaching 0, okay? One very, very common example of a differential is using it to determine the slope of a curve, or the slope of a line tangent to a curve. I think we may have done this example before if you've done any of my other math reviews, but if you have a curve and you would like to know what the slope is of a line that's tangent to the curve, in other words, a line that only touches one point in that curve, then we could find that slope by looking at a differential of that curve. In other words, if I were to just zoom in, take this portion and zoom in as much as possible, right? Let's say that I zoom in, I don't know, 100 times. At 100 times, my curve is going to start to look less like a curve and a little bit more like a line. You can still notice that it's a curve here, but it's starting to look a little bit more like a line. Now, if I were to zoom in even more, so I'm going to take a smaller portion and then zoom into this smaller portion a lot more, my curve is going to start looking more and more like a line. Now, here's the thing. The curve is going to start looking more and more like a line, but no matter how much you zoom in, it will always be a curve, as long as you can quantify the rate at which you are zooming in. Now, the concept of differentials means that if you zoom in to the point where you're almost looking at nothing, but you're still looking at something, at that point, my curve will essentially function like a straight line. I won't really be able to notice or see the curve anymore. All I'm going to see is a straight line. Now, you may be asking yourselves, why is it important to do this? Like, well, why would we do all this? Well, the whole point of doing all this is that once our curve becomes a line, then all it takes is a little bit of geometry to actually find out what the slope is, what the slope of the tangent curve is. Right? Once my curve becomes a line, I can apply something like the Pythagorean theorem in order to figure out what the slope of my line tangent to that curve is. In this example, we can look at very simple. Let's say that this curve is in the xy plane, which means that at this point where everything is zoomed in as much as possible, so much that the curve functions like a line, all I'm doing to find my slope is looking at the difference between these points. Yeah. I thought I heard someone. I'm just gonna mute you just a little bit. Not a little bit. I'm just gonna mute you for now because I thought you were speaking, but I guess you're not. So here's the thing. When we move from one point to the other, now we can look at things in terms of differentials, because now we can say that in the x direction, we're moving a small quantity. And the question is how small? Well, really, really small, right? So small that we can't really quantify it. I can call this dx. And if I were to move in the x direction, that small quantity, the result would be a change in the y direction, which will be my function. That's really, really small. Again, so small that I can't quantify it. So I can call that change dy. So we have two very, very small changes, so small that we can quantify them. Why do we care about that if we can quantify them? Because even though we can't quantify the changes themselves, what we can do is quantify the slope or the ratio between those changes. So even though dx is a very tiny, very small change and dy is a very, very tiny, very small result, the ratio between the two is not going to be tiny. It's going to be a finite number. And that's really why we are using differentials and why we're going to use differentials throughout this entire class in order to actually study, right, fluid mechanics and different fluid properties. Okay, I know that for a lot of you, this is stuff that you've already learned before. So bear with us. We will get to the more important stuff either today or Wednesday. Now let's talk about some stuff where I've noticed based on quiz results, I've already noticed that students are trying to fill in. What happens if a function depends on multiple variables? Okay, so what if, Jesus, I need to improve my handwriting when it comes to the computer. What if a function depends on multiple variables? Okay, so when a function depends on multiple variables, things are going to get a little bit more complicated. Geez, not sure if you can hear it, but one of the things about working on a campus that's right next to an airport, the military airport, is that we get planes all the time. Tech students, I don't think you have to worry about that. All you have to worry about is the shootings and all that stuff that happens in Atlanta. But here at Kennesaw, it's more of a noise that bothers us. Okay, so what if a function depends on multiple variables? In this case, our work becomes a little bit more complicated, but not really impossible. When a function depends on multiple variables, then we can look at change in two different ways. We can look at change as a partial change, or we can look at change as a total change. And analyzing changes in terms of partial terms or total terms, it's actually not that complicated. So I'm going to start by defining what a partial change is. And then later, we're going to see how we can use partial changes to actually find total changes. Now, a partial change is what happens to a function when only one variable changes and all others are kept constant. me just write down this definition here. Only one variable changes. And all others are kept constant. By definition, right, because we need to specify which variable is changing, that way we know which other variables are constant, then a partial change can only really be expressed in the form of a derivative. For example, if I have a function f, and f is a function of a, b, and c, so a, b, and c are three different variables, and they all affect my function f, which is my dependent variable. If I want to know how f changes, when only a changes, I can express that partial change with this expression, where this little squiggly d just means a partial change, not really a total change. Some people call this the dou, some people call it dou. I prefer to go with dou, but you'll hear professors call it different things. In this case, dou f over dou a means how does f change, or tells me how does f change when only a changes and b and c are constant. B and c are constants. Okay, so this change looks at only a partial change. Can you check the door? There could be a student back there. All right, this only looks at change when B and C are constants. Hey, how can I help you?
Hey, I'm here for office hours for David Reyes.
That's me.
Yeah, sorry.
Yeah.
Am I at the right time? Is this a good time or?
So I'm actually giving a little class right now.
Oh, I see.
So I'll be done around 2:45. Okay, so you can stop at that time.
All right, thank you, sir.
All right, no problem.
Thank you.
Sorry about that. I should have put like a message on my door or something. All right. So this partial change is how f changes when only a changes and b and c are constant. I know you've done this before. You've probably done this many times, but let's just look at a very basic example. Okay, I'm just going to say that f is equal to 2a plus b squared plus, give me a number.
20.
20? Okay, plus 20 cosine of c. There we go. Nice random function. If I want to find out how f changes when only a changes, that means that I got to treat b and c as constants, which means that my derivative will be the derivative of this term with respect to a, which is just 2. The derivative of this term with respect to a, but there's no a here, right? And b is a constant. And what's the derivative of just a constant? 0. 0, good. And again, the derivative of this term, which we have 20 cosine of c. Again, c is a constant, so the derivative of a constant is just 0. I think this is a relatively easy concept for you all to grasp. All you have to do is look at all your variables as if they were constants, right? And only look at the variable that's changing. I do see students kind of circling in and out. So let me just post that attendance sheet again so that everybody can have their attendance marked. So I'm going to post the attendance sheet on the chat once more. Be sure to fill out your attendance for today. Okay. We can easily find the partial derivative of f with respect to b. Again, here, a and c become constants, so the derivative of this first term is 0. The derivative of the second term is just 2b. You understand that? The derivative of the third term is 0, so that derivative is just 2b. We can do the same thing with c, but this is not really a class about numbers or looking at numbers. As long as you understand that a partial change or a partial derivative is essentially the change of a function with respect to a variable when all the other variables are constants, then you should be able to tackle any partial derivatives in this class. And there are a lot of partial derivatives in this class, okay? Now that we understand how partial change works, okay, I would like to look at the concept of a total change. Okay, so we've talked a little bit about partial changes. I want to talk now about total change. Sometimes this is called ordinary change. Oh, looks like I can't really move any further here. This is kind of lame. Sometimes we call this ordinary change. Sometimes we call it total change, but I'm just going to call it total change. Okay. Now, whereas a partial change only depends on one variable, all the other variables are constant. When it comes to a total change looks at all the possible ways any variable in a function can actually influence that function. I think it's better if we actually look at this concept with an example. When you start covering the velocity field, you'll find that in fluid mechanics, the velocity vector field, right, is going to be a function of position as well as time. What this tells me is that at most, we're going to have 4 variables that are going to influence or affect our velocities. Okay? So if I want to find the total change of velocity, I need to figure out how each of these 3 variables, position, as well as the 4th variable, time, can actually influence my velocity. Now, we can do this by first trying to figure out what a differential of velocity is. Now, remember, this example doesn't just apply to velocity. You can apply it to any function as long as you know what the variables in that function are. I know that at Tech, you always use an underline to represent a vector. I like to use this little arrow for my vectors, but I feel like all the professors I've seen at that school, they use underlines, which is fine, but I prefer to use arrows just to just to let you know, this underline doesn't mean that these are vectors, okay? Anyway, if I want to find the change, the total change in velocity, then I'm going to have to look at what a differential in velocity looks like. In other words, a tiny, tiny, infinitesimally small change in velocity. There's a little bit of a formula for this, and you can memorize the formula, but I would like you to memorize the concepts as well. So first, for a tiny change in velocity, right, for an infinitesimally small change in velocity to occur, that means we need to have an infinitesimally small change in one or more of its variables. In other words, the only way we can get dv, the only way we can get an infinitesimally small velocity change is by getting an infinitesimally small change in x, or an infinitesimally small change in y, or an infinitesimally small change in z, or an infinitesimally small change in z, or a combination of those. We cannot have differentials when our changes are not also infinitesimally small. In other words, if my time changes from 0 seconds to 1 second, then it is no longer an infinitesimally small change, which means that our velocity change will no longer be an infinitesimally small change. Okay, so let's keep that in mind. In order to have a differential for anything, your variables can only have differentials as well, differential changes as well. They cannot have finite changes. So in this case, we're going to have to look at how the velocity would change if one or more, or in this case, all of the variables were changed while keeping the others constant. Let's suppose that we have a change in x of dx, a change in y of dy, a change in z of dz, and a change in t of dt. We want to ask ourselves, how does that actually affect the velocity? How does the velocity actually change? If you're doing the practice quiz for quiz number 0, Georgia Tech students, then this is actually the first question of the practice quiz, right? Looking at how that velocity changes, okay? So the formula is actually not that complicated. You see, in order to see how velocity changes with respect to one or more of these variables, all we have to look is how the velocity would change if only one variable would have changed if the others were constant. In other words, let's start with x. To look at the change in v, all we have to do is ask ourselves, how does v change when only x changes? Okay, all others are constant. How does v change when only x changes? Everything else is constant. Now that's only the change, right? If we look back up at our slope example, this dy over dx, or in this case dv over dx, is only a slope. And a slope is not really a change, right? So all the slope tells me is the rate of that change. So if we want to turn this rate of change into an actual change, all we have to do is multiply it by however much x changed. And we know that x can only change an infinitesimally small amount, a dx amount. So all we have to do is multiply our partial, which is our slope, times dx. Now you may not really understand this very well, so let's look at this if velocity was only a function of x. So in the case of velocity being only a function of x, then a differentially small change in velocity would be equal to dv over dx times dx. And notice that all this leaves us with is an infinitesimally small change in velocity. Now, I don't want you to kind of take this definition and somehow apply it to partials, because partials do function a little bit differently. However, the concept is still there, at least dimensionally speaking, the concept is still there, right? You have a change in velocity with respect to a change in x. So if we want to transform this slope into an actual velocity value, we just need to multiply it by however much we changed our x value. Now we have a problem here. What I gave you was the change in velocity when only x changes. But we have other variables. So all we have to do now is add up all of our partial changes so that we can find the true or total change in velocity. So when it comes to y, all I need to ask myself is, how would velocity change if only y changed? And then multiply that slope times the change in y. Again, so it's almost like a superpositioning principle, where we're looking at different partial changes and we're just adding them up to get the total change. We don't really call this superpositions, and don't quote me on that, but the concept is similar to the concept of superposition, right? Where you calculate different things individually and then you just add them up. We can do the same thing with z, where we ask ourselves, how does v change when z changes? And then multiply that by the actual change in z. And we can do the same thing with time, where we ask ourselves, how does velocity change when time changes? And then multiply that by the change in time. My lines are important here. Notice that these are partial changes, so I'm using the squiggly d. And this is an infinitesimally small change, so I'm using just the lowercase d. Let's keep that in mind, that the lines are actually important here, okay? Let me just get rid of this. This tiny formula applies for any function that has multiple variables, not just velocity. In this class, you'll use this for pressure, you'll use this for stress, other types of stress, for forces, etc. Okay. Now all this tells me is what a tiny, tiny, tiny change in velocity would be. In the practice quiz, I ask you, or the quiz asks you to figure out what the acceleration of a fluid particle would be. Now, I don't think I have to explain that, but just in case, acceleration is simply a change in velocity with respect to what? Time, that's correct. Now, here's the thing. You already know this formula. You already know that to get the total change, all you have to do is multiply the partial changes times the infinitesimally small quantities. So all you have to do to find dv over dt is take this formula and then derive with respect to dt. So all I'm going to do now is write down all my terms. Oops, this should be an x. Ugh. Okay.
I have a question.
Yeah, of course, go ahead.
I think somebody else asked the question in the chat too. It was pretty much, can you just explain the difference in the D's? The squiggly D and a straight line D, or yeah.
Oh, of course. Yeah, sorry, I wasn't paying attention to the chat. Should have paid more attention. So right now I'm using two types of letter D's, right? The lowercase d stands for a differential, which means this is a very, very, very small change in something. Now the partial, right, which is called the dou, the dou, whatever you want to call it, is also a very, very, very small change. However, it is only a small change with respect to one variable. Small change with respect to only one variable, and then all others are constant. These differences are only aesthetic differences, okay? This is just a definition that we're giving to these two variables. It's about 2:40. I do want to finish this, but I will have to finish it on Wednesday because for some reason I have some students waiting outside. But hopefully we understand the concepts. On Wednesday, we're actually going to start looking at numbers. Okay, we're going to take these concepts and we're going to apply these to vector calculus, differential equations, etc. I'm using the free version of Zoom, so it's going to close automatically. So before it closes, I'll just say thank you everyone for attending. If you have an appointment, just re-sign, just re-log into the same link, okay? And we'll continue on Wednesday. And I'm going to upload everything I can this week, okay? Thanks everyone for attending. Have a good one.